So let's move on then from the literature reviews and just review a couple of things here that we talked about last time. We talked about solutions to the block function, and there were two that we considered. One is where k, this momentum vector, is equal to 0, and another one where it's equal to pi over a. And if you plug that k into the block function, k equals 0 gives you 1. Um, or sorry, e to the 0, e to the k, ends up being 1, and so this function is just the sum of all those basis functions without changing sign. The solution pi over a gives back a plus and minus sign alternating as you jump from one function to the next. So you can see the symmetry of the orbital changing. And so the solution of the block function for pi over a is this totally antisymmetric combination, whereas the k equals 0 combination is the one where the basis orbitals don't change sign. And so the k equals 0 solution for s orbitals is bonding, and the k equals pi over a for s orbitals is antibonding. But now if you do that same thing for p orbitals, you get a different result. K equals 0, where they don't change sign, shows an antibonding interaction between each p orbital, and the k equals pi over a1, you have this orbital changing sign as you jump from one to the next, and this flipping as you jump back and forth or from one to the next gives you bonding interactions. Okay, so whether those block functions are, the energy of those things differs depending upon what the basis function is. Okay, so we talked about how in the case of the p orbitals, the k equals 0 solution is the high energy one, and the pi over a is the low energy one. And the s orbitals, it's the reverse. And then we looked at a few examples with d orbitals, and you can see the sigma bonded ones run from low energy to high energy as k goes from 0 to pi over a. The pi bonding ones go from high to low, and the delta bonding ones do the opposite. They go from low to high. And so you can look at all of these diagram, this E versus K diagram here on the right, and conclude the symmetry of the kind of orbital that's involved just by looking at which direction it runs on the diagram. All right. All right. So, and then we really briefly talked about the fact that K is also directional. Okay. This is important, and it makes these diagrams more complicated. So let's just start here more carefully talking about, excuse me, talking about a square lattice of s orbitals. Okay, so there are a bunch of s orbitals shown on the left there, all spaced out with a regular distance. And you can consider how k varies in the x and the y direction. Now, this particular solution for the block function is one where kx and ky are both 0. And so if you go along the x direction here from left to right, you'll see the orbital isn't changing sign. It's just the sum. And the same is true for y. You go along the y direction, they aren't changing sign. And so this orbital is the totally bonding combination. But there are many others, and depending upon the direction that you look in the lattice, if you just want to look along what happens as you vary k along the x direction, that would be here. If you want to look at how k varies along the x and y direction, that would be here. This box here represents the unit cell of this lattice. The unit cell of this lattice is just one square of the lattice. And you can see how k propagates along unique directions in the unit cell. That might not mean a lot to you yet. We're going to do that more thoroughly here in just a few minutes. But the directions the directions that are relevant, the unique directions in this crystal of s orbitals, give rise to their own Brillouin zones. Okay, so shown on the right is an E versus K diagram, and gamma this symbol down here represents kx and ky equal to 0. Okay? X, this point right here, represents kx equals pi over a and ky equals 0. And then m here equals kx and ky equal pi over a. Okay, so you can look at how the vector varies from kx and ky equals 0 to kx equals pi over a and ky equals 0 to both equal pi over a. You notice these 2 points are the same. These guys actually kind of, you can fold on, you can roll this thing up and touch the ends. This is the same point. It's just shown on opposite ends of this diagram. So you can watch what happens if you vary the k values at the same time, headed toward pi over a for both x and y, or if you just do one and then the other. Okay, so let's take a look here at some of these other points just to sort of spell that out a little bit more clearly. So let's take a look at the x point, all right? The x point here is where only kx, oh, we have a question. What is the y-axis of the graph on the right? The y-axis of the graph on the right needs to be labeled. That's energy, just like these guys are energy, okay? It's the same sort of a diagram here. The y-axis is energy and the x-axis is k in two different Brillouin zones, okay? Gamma to x and gamma to m, where the k value is changing from 0 to pi over a. So you can look at how energy evolves as kx and ky are varied from 0 to pi over a this way. So let's take a look at the unique solutions at the x point and at the m point. Okay, so at the x point, you're just going horizontally. Only kx is changing. Ky is not changing. And so x is equal to pi over a. Kx is pi over a, and ky is 0. Okay, m, both x and y are changing. And so the m point is kx and ky equal to pi over a. There's another x point where ky is equal to pi over a and kx is equal to 0. Okay, and you know it's identical to the other one. It just has a different orientation, which in a square lattice is equivalent. Okay, so let's just take a look at this wave function a little more closely now. So in the ky equals 0 direction, it's just the sum. It's the sum. The s orbitals are not changing sign in the y direction. But in the x direction, where x is equal to pi over a, the orbital basis is changing sign. Right? And we know for just a linear chain, when k is equal to pi over a, you go from plus to minus to plus to minus to plus to minus to plus to minus. When it's 0, it's just plus, 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 plus. So this function here, this wave function for kx equals pi over a and ky equals 0, you can see that the wave function is oscillating in the x direction and it's constant in the y direction. The wavelength in the y direction is infinitely long. The wavelength in the x direction is 2 unit cells. All right, so let's go take a look at the m point. The m point is where both x and y are varying. So start down here in the lower left. If you want to look at ky, go in the vertical direction. It varies at each point. Kx also varies at each point. And then if you move here and you go up, it varies at each point, and so on. And so this m point for both kx and ky equals pi over a, you get oscillations or wavelengths in both the x and y direction that are equal to 2 unit cells. And then again, another version of the x point here where y is pi over a and x is 0. Now in the y direction, it varies at each and in the x direction, it's just constant. Okay, so you can see that in a square lattice like this, there really are two vectors of interest, x and y, and you can look at how the wave function varies as you go from the uh, x and y equals 0 solution and other solutions where either x or y or both equal pi over a. And then that gives you this diagram, a couple of different Brillouin zones. And of course, this point here, the M point, where both the x and the y direction are pi over a, is the most anti-bonding combination. It's anti-bonding in all directions at any given orbital. Its nearest neighbors are out of phase. These two x points, the nearest neighbors are in phase in this direction and out of phase in the other. So it's intermediate, okay? So most bonding, most anti-bonding, intermediate. You go look at your plot here and you see the most bonding, the intermediate one, and the most anti-bonding ones. All right, so let's take a look at one more solution here. So we just did the x, m, and x solutions. Now let's do the case going along the x direction, but where x is not pi over a, kx is not pi over a, but kx is pi over 2a. So you can think about this for a minute, and you can go and plug all these numbers into the block function if you want. But another way to think about this is that the wavelength of this um, orbital, or its, I guess the wavelength of this orbital is twice what just the kx solution is. Okay, so here, whoops, yikes, sorry about that. I wonder if there's where's my pointer? Well, so you can see here, these solid points represent nodes. And so as you go from plus down toward minus, it traverses 0 at these nodal points. So this wave function is longer. The wavelength here is 1, 2, 3, 4 unit cells instead of 1, 2 unit cells. Okay, so this guy, as you go from the all bonding combination where kx or ky is 0 toward pi over a, halfway there you get to pi over 2a, and that wavelength is 1/4 as long. Sorry, that wavelength is twice as long, and the energy is half. Let's just go back to the diagram. I guess we'll do that in a second. Let's do that again here in the x and y directions. Okay, so here you see the same sort of oscillation that you see in this solution for pi over 2a, but now it's in both directions. And that gives you this kind of a lattice here. You can see that it's undulating the wave. Why is this? Oh no, I must be on the wrong account again. How is that possible? All right, we're going to finish this and then I'm going to try and fix my account. Okay, so the important thing is that the pi over 2a solution is halfway along this plot. So take the x direction, take this x point here. This x solution is for pi over a. This pi over 2a is right in the middle. Okay, it's halfway to being pi over a. So it falls right in the middle. And you can see how, because the wavelength is longer for this wave function, the energy of it is not going to be quite as high. This is halfway there. It's sort of like E alpha in the linear chain of hydrogen 1s orbitals. Okay, and so you can also do this kx and ky are pi over 2a that, where would you be? That would be this orbital here, or this particular energy, this region of the Brillouin zone between gamma and M. Okay? All right, so K, this index, is a vector, and it depends upon the direction, or it's related to the direction in the solid. And you have to consider the symmetry of the solid to get to the allowable values of K, the unique values of K. And so this particular symmetry is a square lattice. And so it gives a few unique solutions. More complicated crystals have more complicated solutions. So K is related to the wavelength of the electron, or the wave function, and its momentum. So you can see down there in the pi over 2a solutions, the wavelength is twice as long as the pi over a solutions. And so, the energies are going to be related to that wavelength, okay? Let's see here. Right, when k equals pi over a, the wavelength is minimized for s orbitals. All right, so those E versus K diagrams allow you to see how energy levels change as you go from the various points on these diagrams. Now, another complication that you'll sometimes see here is that people don't always, the basis orbital that you choose for your diagram will also influence the result. So far we've chosen atomic orbitals as our basis function, but you can also choose small molecular orbitals as your basis function, okay? So on the left-hand side, you can see here, for example, the single orbital basis, where you're just taking s orbitals in a chain and combining them. At 0, it's down here. At pi over a, it's up here. At pi over 2a, you get orbitals that look something like this. But if you want, you could use a 2-orbital basis. Okay? And so, for example, let's pretend that this is a chain of ethylenes or something. A chain of an infinite ring of carbon atoms with p orbitals pointing up and down. And then you could think about these as looking like pi and pi star orbitals. And you could make linear combinations of those pi and pi star orbitals. So, if your orbital basis is pi and the k equals 0 solution doesn't change sign, the k equals 0 solution also doesn't change sign when your orbital basis is pi star. Okay. And so if you choose this basis, then the k equals 0 for these two is different. It runs up as you go away from k equals 0, starting from this basis, and it runs down as you go away from k equals 0 if you start with this basis. And in the intermediate position, you get something like this. Now, you can think about this as kind of like increasing the unit cell from A to 2A, if you like. And so you can see how this pi over 2A solution here looks just like this one. Okay, so these give you the same wave functions, but the diagram ends up looking different, okay, because of the change in the unit cell dimensions. And Hoffman says, this is kind of like drawing out the single orbital basis function on a page and folding it in half. It gives you a different looking diagram folded in half at this new value of the unit cell dimension, which is twice the original one, okay? So just like in any other molecular orbital diagram here, the number of bands in the band structure that you get is equal to the number of units that are a part of the unit cell in the case of a solid. So you have 2 orbitals in the unit cell. Here are 2 hydrogens or 2 pi symmetry orbitals. This gives you 2 bands. There's one band, there's another band. Here you have a single orbital, and then you have a single band. Okay, so the number of bands that you see is equal to the number of orbitals that are in the unit cell. All right, so let's take a look at another case. Here's a question. What is the advantage of changing the length of the cell? I don't know how to answer that, Caitlin. I think that that's a perfectly good question. People often do it when talking about pi orbital systems like graphene, which we're going to talk about here in just a second, or polyacetylene. And, I think it sort of depends upon the type of how you want to think about the bonding of the system. It's kind of like, do you want to create a diagram using hybrid orbital basis functions or like sp3, or do you want to use atomic orbital basis functions like s and 3p's? It's sort of arbitrary. Sometimes it'll help you get your point across better than others. Let's take a look at this. Oops, there we are. Let's take a look at this example of graphite. This shows the gamma, m, and k points. Eesh. These pictures show the gamma, m, and k points for graphite, and you can see the symmetry of the graphite lattice shown up here in the upper left. And in this example, we're going to use pi and pi star basis functions instead of just a single p orbital basis function that has pi symmetry. So you're looking down on the pi bond. You're only seeing the top lobes of this pi bond, and so there's the combination that's bonding, and then there's the combination that's anti-bonding. And we're going to look at how they vary along x and how they vary along x and y. Now notice that the m direction here, or the m point, and the direction headed toward the m point, is not where kx and ky are equal. It is some other ratio, and what's important is that those functions are varying along the crystallographic direction. So we're going to see that here in some of these guys. So let's take a look down in the bottom set of three pictures. You have the three different points, gamma, m, and k. Gamma is still kx and ky equal to each other and equal to 0. Okay, so along, in this case, k is 0 in both crystallographic directions, and so you can see the pi orbital basis does not change sign. Okay, so now if we take a look at the m point here, the pi orbital basis is switching. If you go and say take this pair here and you go this direction, you'll see that the pi orbital basis is switching, and in any direction in the crystal that you choose, you'll find that it's following the crystallographic axes. That as you jump from combination to combination, it's varying back and forth. It's kind of hard to visualize this one here, the k direction, where that pi orbital basis is alternating sign as you go horizontally. But this is a calculation showing you exactly what it looks like. So let's go up here. Here is the pi star basis, right? So pick these two, let's say, for our example. And is that the best pair? Let me see, I've forgotten now exactly which one to choose again. Well, we can pick this pair here. The gamma point, all of these guys are pi star along each individual direction. And now if we take this pi star orbital and we jump up here, just like we did in the case below, now the sign of that pi star orbital is flipping from minus plus to plus minus. Okay, so the sign changes along this direction. and it doesn't along that direction. Now here in K, again, you get this funny result that's pretty hard to visualize on your own, but is the result of a computation. So let's take a look at these Brillouin zones now, just for the pi and the pi star orbital combination. I don't know what happened to my pi star labels here to fix those. So starting down here in the gamma point, again, the pi bonding basis, this one here, the k equals 0 solutions along both crystallographic directions, that's a totally bonding combination. So this wave function is clearly going to be the most energetically favorable one, or the lowest energy wave function. And likewise, the k equals 0 solution for the pi star orbital basis is the most antibonding one in each direction that you look. For a given p orbital, you see antibonding interactions. Here you notice an intermediate energy. There's some bonding interactions this way, some antibonding interactions in this axis, some bonding interactions here, some antibonding interactions there. And then these guys with the nodes next to each one of these orbitals kind of look like they're relatively non-bonding. Okay. So if you look at this diagram, here's the gamma point. You can see that the pi orbital basis comes all the way down here to alpha plus 3 beta. And the pi star orbital basis comes up here to the highest possible point. And then the M points here, you can see are intermediate. They have just some anti-bonding character and some bonding character. And this K point is actually right in between. It sits right at E alpha. This orbital is approximately, essentially, non-bonding. Okay. So you can see all of these different bands and combinations as you look along different, or you look along the various crystallographic directions, and you consider the magnitude of K, or the wave length, along each of those directions. Here's a slightly more complete diagram shown on the right. So we have the pi and the pi star orbital basis, and we've also thrown in the sigma framework here. Carbon-carbon sigma bonding is also part of the same diagram, and it comes way up here. Notice now the Fermi energy marked in this diagram is this dashed line, and it touches these bands right here at K. Okay, so if you were to say which of these orbitals is filled and which of these is empty, well, many of them are filled and empty. It's the electrons in graphite or graphene fill up the bands right up to the Fermi energy, which happens to be at K. Okay, so this orbital here is the highest occupied orbital in graphene, and these bonding combinations at the K point are also filled, and this gamma point orbital is empty, and this one is filled, and these M orbital points are filled, filled and I guess possibly empty. And so you can look at these diagrams and say something about which orbitals are relevant. And in particular, it's really important to notice where the Fermi energy is, and at what point in the diagram and what type of orbital is occupied. All right, so in fact, people will often draw these diagrams out in X and Y directions and show what they call these Fermi surfaces, okay, plotting out for the benzene, or for this hexagonal lattice, how the energy evolves as K and Y change. And you get this really fun looking pattern here that crosses 6 different times, where this upper and lower band touch right along the points of the hexagon. These two guys get close to each other, the surfaces cross, and that's right at these K points where that crossing happens. So you'll see diagrams like this. This is a 3-dimensional representation of this 2-dimensional diagram, considering both the X and the Y directions on the same sort of a plot. All right, so there are many different types of crystals, and we're not going to get into this really, but people are interested in knowing um, about those various directions and the various how the wave functions evolve along those directions, often because they're interested in understanding the properties of crystals as they evolve in different directions. For example, a crystal can have conductivity that differs as you look at different directions. You can measure the charge transport mobility along one of these crystallographic directions and compare it to another one, and you'll find different values. And that's because the bonding, the electronic structure of the crystal differs along those different directions. The magnitude of the orbital interactions differ along those different directions, and that gives you different values of beta. It gives you different bandwidths and different curvatures. And so solid state physicists keep track of all these, and they make these Brillouin zone diagrams labeled with all these points and usually with Greek symbols. Um, and you have to just understand that they represent different crystallographic directions in the solid. And so you're mapping out the wave functions in space that way. All right. Whoops. So just a few conclusions from this section. Um, so crystal orbitals are made up of linear combinations of atomic orbitals, and the block function makes it easy to describe how they vary with using this index k. Okay, and so they treat the k value as kind of a quantum number for the wave function. It tells you about the wavelength of the electron or its momentum, right? The momentum picture is the kind of classical description of the electron, and it's related to wavelength by de Broglie's relationship. Of course, this k is really a vector. Not only has a magnitude, it has a spatial component that's mapped onto the unit cell of the crystal. And I think we've said this enough, but I'll repeat it. The width and energy for those bands is really dependent upon that orbital interaction strength, which is dependent on orbital overlap. And that's dependent upon direction and the basis function and all of the above. Okay, so all of these things interact to give you very interesting looking band diagrams. All right, so I want to spend a little bit more time talking about these band diagrams now and relating them to the free electron model. Okay, so the free electron model treats electrons and solids like they're particles. You can describe the energy of those electrons in terms of their potential energy and their kinetic energy. We're really interested in the kinetic energy. The potential energy piece is really about the ionization energy of the electron. It's sort of like, the energy of the electron relative to vacuum when it's at rest. And then the kinetic energy piece is really about the velocity of the electron, or its momentum and its wavelength. And so, um, you can relate those things using the sort of early quantum mechanical ideas. Here, kinetic energy is 1/2 mass times velocity squared, which is equal to momentum squared over mass. And that momentum can be related to the quantum mechanical momentum using the de Broglie relationship, and it gives you this kinetic energy is equal to h bar squared k squared over 2m. Okay, so these are simple things that fall out of quantum mechanics and basic tenets of quantum mechanics. And what it really says is that the kinetic energy of the electron varies with k quadratically. Okay, so this happens to be a relatively good approximation. So if the free electron picture of the electron energy on an E versus K diagram is approximately quadratic. So E varies with K squared. And this works pretty well near the near the bottom of the bands. Okay, so near where um, the bands equal k, where k equals 0 in the band structure. Okay, so you get this quadratic relationship under those conditions. Um, and as you go away from k equals 0 to pi over a, the binding of the electron to the lattice changes, and that changes the evolution of the energy with momentum and makes it no longer quadratic. Um, but this is a sort of simple approximation that turns out to be pretty useful. And so you can replace that kinetic energy term here with h squared k squared over 2m. So at the bottom of the band, z versus k is this kinetic energy piece plus the potential of the lattice. And then here what I've done is I've set that energy here, describing it as a free electron, to the energy that comes out of the periodicity description of the MO energy, so the linear combination of atomic orbitals model. You just say, all right, let's pretend those two things are equal, um, and you can assume when k equals 0, where there's no kinetic energy, that the energy of the crystal is really kind of like the most bonding combination of orbitals. It's the lowest energy combination, and so we can assume that the potential energy at that value of k is alpha plus 2 beta. And if you take this term here and expand it as a power series, you'll come out with this h squared k squared over 2m is equal to the orbital interaction times ka squared. Or rearranging here, you can end up with the orbital interaction strength is really 1 over the mass of the electron. So that's sort of a lot of assumptions and math tricks and stuff like that that I'm not going to spend any time on. But what it's telling you here is that the orbital interaction strength and the mass of the electron in this kind of a picture are related to each other. And that sort of took me a little while to wrap my head around. We're going to talk about this in a little bit more depth to sort of see how physicists use this language to describe beta. And physicists spend a lot of time talking about effective mass, okay, which is actually m star. And m star is sort of a fudge factor because this equation doesn't really work very well. If you just plug in the mass of the electron here, what you'll find is that that's not really beta. And so they say, okay, well, that says that there's something different about the material that's changing um, um, the effective mass, and that is somehow related to the influence of the binding of the electron to the lattice. And so we're going to use a fudge factor called effective mass to relate this orbital interaction strength to the free electron picture. Okay, so let's not get too worried about all the justifications for that because it takes too long to really work through it all. But what physicists will often say is that in a band where beta is large, in other words, in a band where the orbital interaction strength is really strong, that the effective mass of those electrons must be very light. So the fact that the electrons are light means that they move around quickly, they have long wavelengths, and they do not interact strongly with the lattice. Okay, so the mass of the electron sort of tells you about how deeply it falls into the wells at each at each nucleus, and how tightly it is bonded to that lattice. An electron that's light flies around very easily, is not very strongly bonded to that lattice, and it happens to be the case that that is in bands that have very strong orbital interactions. So to help drive this sort of thing home, you can take a look at something like the curvature of the E versus K diagram. So take this relation I showed you before. So here's the kinetic energy term for an electron. That comes from the simple classical quantum mechanical conversion. And if you take the second derivative of that with respect to k, you end up with a function that's proportional to 1 over the effective mass. Okay, so second derivative of an E versus K diagram is really the curvature of that diagram, right? It's related to 1 over the mass, or in other words, these two guys are inversely related. The effective mass is inversely related to the curvature of an E versus K diagram. So just to help make that clear, here are two different E versus K diagrams. This one has a small bandwidth, this one has a large bandwidth. This one has a small curvature. This one has a much larger curvature, okay? And that curvature here is inversely related to the mass. So for a low curvature, the effective mass is large and the electron likes to sit still on the nucleus, where the curvature is much greater because the bandwidth is larger. It's a sign that the electron is very light here because they're inversely related. Strong curvature means small effective mass. And an electronic band like this, the electrons that are in it have a weak interaction with the lattice and large kinetic energy. Okay, so you can look at an E versus K diagram and say, all right, strong orbital interactions here, weak orbital interactions here. And these electrons then, they're much more likely to be stuck to the lattice, resting in the potential wells that each nucleus provides to that electron. And so they have a low effective mass, low kinetic energy. These ones are going to be delocalized, spread out in the crystal, not sitting on any given atom, but running around the crystal. And that's a consequence of the fact that the orbital interactions are strong and the curvature of the E versus K diagram is quite visible. So just by looking at the bandwidth and the curvature of those diagrams, you can think about the electron's motion and how fast it moves, or the kinetic energy of that electron in that crystal. So let's see here. Let's just take a look at a table of effective masses. All right, so now these are normalized effective masses. So what we've done is we've taken the effective mass and divided it by the actual electron mass. And that ratio tells you, how heavy it is. So a small number is light, a big number is heavy. And if you look at all these different semiconductors here, I've shown effective masses for holes, or the absence of an electron, and effective masses for electrons. These tend to be holes sitting at the top of the valence band, for example, and these tend to be electrons sitting at the bottom of the conduction band. And so what you'll find are a number of very interesting trends. One of which, for example, is that electron effective masses tend to be lighter than holes. Say cadmium selenide or gallium nitride, the hole masses are 0.6 and 0.45. The electron masses are 0.19 and 0.13. Does anybody have a guess as to why that would be the case? This is a tricky question, but it's a good one.
Does that imply that holes are more localized?
Yes, in a sense. They are more tightly bound to the nuclei. In fact, the wave functions in a bulk crystal are infinitely extensive, spreading out completely. But if you look at the wavelength of the electron and you look at the amount to which it's concentrated on a nucleus, the heavier ones are more concentrated on the nuclei. The lighter ones are more spread out between the nuclei. So localization is not really the right word in solid state physics parlance, but I think that that's a good way to think about it. the electrons are more spread out and not, um, it's just sitting on the nuclei, but also in between them. Why would that be? So I just showed you um, how mass relates to curvature, right? So what does this say about the curvature for holes and electrons? And curvature is related to bandwidth, right? Something with a really broad band has a higher curvature. If the band is really flat, it's not highly curved. If it's really flat, the electrons are heavy. They're sort of more localized, so to speak, on the nuclei. And that's a consequence of what kind of an interaction? The orbital interaction, the beta. Right? So when the orbitals get together and they make a connection to each other, the better the overlap, the stronger the interactions, the broader the bands, the higher the curvature, and the lighter the electrons. The more spread out they are, the more the wave functions sit in between the atoms. So when I look at these numbers and I see that electrons are lighter than holes, it means that their wave functions are not just sitting on top of the nuclei, but also in between the nuclei. And that implies that the bonding for the wave functions that carry the electrons is different than holes. So if these are electrons sitting in the conduction band of this material, and this is for holes sitting in the valence band, then you can look at these numbers for the effective mass and say something about the bandwidth of the conduction band and of the valence band. So on the right, you can see the effective masses of electrons in the conduction band is much lighter than the effective masses of holes in the valence band on the left. And this is a consequence of the orbitals that are used to make up the conduction and valence band. So take cadmium sulfide as an example. Okay, cadmium sulfide is a salt, cadmium 2 plus, sulfur 2 minus. And the conduction band orbitals then are going to be cadmium-like. The empty orbitals are going to be like cadmium 2 plus, which has no valence electrons. And the filled orbitals are going to be like sulfur 2 minus, which has an octet. And the cadmium base functions are 5s orbitals. The sulfur base functions are 3p orbitals. So the valence band, at the top of the valence band, is going to be made up of sulfur 3p orbitals. And their bonding interaction is going to be weaker than the cadmium 5s orbitals that make up the conduction band, because p orbitals do not make as strong of a bond as s orbitals do. The overlap is poorer. So these differences in effective mass on the right and on the left for electrons and for holes reflect the orbital parentages of the semiconductors. Okay, cadmium 5s gives you a broader band than sulfur 3p, and that's a consequence of orbital overlap. That's a mouthful. That's a lot of arguments all in one, but something that I think we have talked about so far, just in bits and pieces. Does anybody want to ask any questions about that? Okay. You can also look at effective mass tends to follow ionization energies. So if the atoms are very electropositive, then the electrons are not going to be bound very tightly. And in the salt, those electrons, the electrons will sit on atoms with that are electropositive, like cadmium, for example. And the more electropositive they are, the lighter the electrons tend to be. And you can see that going down the series, say from phosphorus to antimony, arsenic, and so on. But the big difference, really, I think the useful one is comparing the basis orbitals that make up the bands. If we had materials in here where the bands are made of d orbitals or f orbitals, the f orbitals don't make strong they don't make strong interactions, and so they would have very flat bands and very high effective masses. All right, so another really interesting example of this is in this graphene band structure that we've been talking about. So the graphene band structure, right at the K point, crosses this pi and pi star orbital basis functions cross right at the K point, and that happens to be where the Fermi energy is. Now, it turns out that at that position where they cross, the bands are roughly linearly sloped. And it gives you this really interesting situation pointed out by Dirac. He said that at this point, where there is linear slope, there's zero curvature. And because there is zero curvature, that means that electrons at that Fermi energy are massless. Effectively, they are not bound to the lattice at all. They are massless, and they have infinitely long wavelengths, and not wavelengths, but their infinite, their masslessness makes their charge transport mobilities really high. So they're not bound to the lattice at all. They have really high kinetic energies, and it gives rise to very, very good conductivity. Okay, so we haven't talked a whole lot about this, but charge transport mobility is a measure of how easily the electrons flow through the lattice, and it's inversely related to this effective mass. Okay, so the lighter the effective mass is, the higher the charge transport mobility is. And right at this point here, where the curvature is effectively zero, these two lines cross. Sorry, I think I said that in a very confusing way. So right here at the top, you can think about this as kind of like the valence band, and this is the conduction band in this semi-metal. And right at this point where you go from flat to flat, the curvature here between these two uh, uh, is infinitely large. Okay, the transition from flat to flat is infinitely large. And so Dirac said that electrons sitting at the top of the valence band in graphite or graphene should have zero mass, and their charge transport mobilities should approach infinity. Okay, and so it's true that in a single sheet of graphene, that if the Fermi energies right in the right position there at the Dirac point, that the charge transport is extraordinarily good. And so there's really an entire field of physics that was born out of studying the transport of electrons in graphite because it had this, or in graphene sheets, because of this very cool relationship between the energy and the momentum. All right, so I want to take a look here at the timing. Looks like we have 5 more minutes. Okay, so I think that took me longer than I wanted. I'm going to keep going here. So we're going to talk next time about the relationship between E versus K diagrams and optical transitions. And from there, we're going to start transitioning into quantum dots. So this is maybe a little elementary, photon absorption in a molecule, the photon energy has to be resonant with some kind of a transition between two levels to get the electron promoted. And this means that you get absorption bands in a spectrum of a molecule, and the peak maximum of that band is very closely related to that energy spacing. Okay, in a semiconductor, because you have many orbitals that are filled and many orbitals that are empty, there are many transitions that are resonant with the photon of different energies. Okay, and of course, the minimum energy to promote an electron from here to here is the band gap spacing. But any energy higher than that, there's lots of allowed transitions. So the absorption spectrum of a semiconductor has this absorption onset, and that onset is roughly the band gap, and then it goes up from there. Okay, um, so semiconductors, these spacings are about 0.1 to 3 electron volts, and in nanometers, that's 12,400 nanometers to about 400 nanometers. If you remember the conversion, that 1 EV is equal to 1,240 nanometers. That's a useful number to remember. All right, so um, you know, the other thing that happens when you photoexcite a semiconductor, you promote an electron, and in a few picoseconds, those electrons tend to relax back down to the lowest level by jumping from level to level in the solid. And the same thing happens to the hole that you create on promoting an electron out of the valence band. The hole that's left behind bubbles up to the edge of the valence band. And this process emits vibrational energy levels, or emits vibrational energy packets, or phonons, in the crystal to cool those charges down. That happens fast, picosecond time scale. And those electrons then sit at the band edges, the conduction band edge, and the hole sits at the valence band edge, and it sits there for nanoseconds to microseconds, depending upon the material, before the electron jumps across the gap. And some of the time, that jumping across the gap produces a photon. And the energy of that photon is equal to the band gap. And so if you have an absorption spectrum for a semiconductor that's photoluminescent, you'll often see an emission spectrum that sits right at the band gap energy, okay, right at the absorption onset. So all of these transitions where you're promoting electrons, the electrons fall down, the holes bubble up, and you get a photon back out right at the band gap energy. Now, let's take a look at this same sort of a situation in gallium arsenide before closing here. Here's a gallium arsenide crystal, and now we've actually shown the conduction band and the valence band here, and the band gap. And the band gap transition is from this band to that band. Um, and I think since we have 1 minute left, apparently, I don't see why this would be the case. But if we'll come back to this next time and finish that material then. So I think that's all I have to say. I'm going to stick these guys back up onto the website. If you guys have any questions about today, I know that's a mouthful. Please come back to me and read the Hoffman article. You're going to start transitioning to the next reading assignment to become familiar with quantum confinement here, starting at the next lecture. And I'll do my best to turn these guys around. Those of you that got your critical reviews back late will get them back early this time, and vice versa. Thanks for hanging in there with me, and I will look forward to seeing you again soon. All right, bye now.